Thanks for the first question. So what I want to hear about atmospheric pressure, you can start with the history. So since, wait, yes. So we live on the surface of the Earth. So above us, there are lots of air. This air, the mass of this air, is more or less equivalent with 10-meter water. It has some other properties which is important, so it contains oxygen for life and so on, but technically for us atmosphere is nothing else, just the pressure you live with. So how can we measure it? Perhaps you can Google the Torricelli experiment. Torricelli experiment said if you take a tube, a closed tube on the top and open on the bottom, and just fill it with mercury and place it in a barrel like something which is full of mercury. The mercury in the tube, the level of the mercury will go down. What does it mean? If you look at one point on the surface of the mercury here, the pressure from the air comes from above, and the pressure from this close to 760 millimeter mercury is the same. This is why we use till now the unit for air pressure is the mercury millimeter. So this is a balance again, the pressure from the air and the pressure from this 760 millimeter mercury is the same. This was the first time somebody measured the pressure of the air. You should say something about barometer, how we measure, but technically you have to know. So the atmospheric pressure is nothing else, just the weight of the air above you divided by the surface of your, for example, body. So if you pick up any square meter on the surface of the Earth, above this 1 square meter we have close to 10 millimeter equivalent, 10 meter water equivalent air, which is 10 tons. If you divide it with the surface, you got pressure, and this pressure is 1 atmosphere, which is 10 to 5 Pascal. So I mainly need the story, weight of the air divided by the surface, this is pressure, and how can we measure it, what was the so-called Torricelli experiment. Its connection to the weather, so when the surface is warm and this warm surface heat up the air, it goes upwards. If it goes upwards, the pressure will be smaller. If the cold air moves towards the surface, that will create higher pressure than the normal 1 atmosphere. So the pressure changes with the weather. When it goes up, for example, the humidity of the air will create clouds and it can create rains. You can measure easily. And what we know, since if you imagine you are on the surface of the Earth or you go upper, the weight of the air above you will be less since you are at a higher altitude, and this changes is 1.2 kilopascal for every 100 meters, and this is what we measured during the seminar. So I need some tale about weight of the air divided by the surface, how weather changes the pressure, how can we measure how the pressure changes via altitude, and so on. You don't have to mention everything, you just have to have some picture in your mind what is pressure, what is atmospheric pressure. Is it okay now? You can also explain these things what we measured. Next one. Foucault, yes. Wait. All right, so this is the non-real forces. So back to Newton's first axiom. It said, in inertial frame of reference, the object remains at rest or move with a constant velocity. If there is no force on the object, it remains in that status. What does it mean, inertial frame? Inertial frame is not true for the Earth because the Earth is a rotating coordinate. So if you live on the surface of the Earth, we are in the rotating coordinate system. Its effect is small. You can't feel it. You can't feel that you almost leave the Earth because of this rotation. It's comparing to, for example, the gravitation. These forces are small, but there are two forces. One is centrifugal forces. If you are in a rotating system, you can feel some forces towards outside of the object, and the so-called Coriolis forces. Coriolis forces is true only for moving object in a rotating coordinate system like Earth. So, for example, if you are here in the northern hemisphere, if you move that direction, you will feel a force right to you. On the southern hemisphere, you will feel the force left to you for the same velocity from left to right. Its formula is minus 2m omega cross v. So if you take your right hand, omega cross v can point the minus 1, can point out what is the direction of the Coriolis forces. It's not that obvious, you can't feel it, but you can show it with the so-called Foucault pendulum. Foucault pendulum was a normal pendulum, but it was a very, very big, very long. So it moved from right to left, from right to left. So anytime you placed it in Paris, it rotated. So this is the plane of the motion. You can imagine the plane of the motion is, for example, the screen. And it rotated the plane of the motion, since if it went from left to right, the Coriolis force, if you place your phone or tablet on the table, Coriolis force point upwards. When it went backwards, it was downwards. So very, very slowly, but it changed its plane of the motion. In Paris, in 24 hours, it changed like 3/4 of the full rotation. On the North Pole, it would change it would rotate one full rotation, and since the property of the cross product at the equator, it does not change the plane of the motion. So Foucault pendulum was an experiment. It was shown in rotating coordinate system, except the centrifugal forces. There is another one, a Coriolis forces, but it works only for moving objects. This pendulum was a moving object, and it changed its plane of the motion. And by the way, by the fact that it moved almost 3 over full rotation, it varies, and we can measure the velocity. Since this is just observation, you can also calculate the omega, the angular velocity of the Earth, by this experiment. You just place a Foucault pendulum somewhere, you can measure how fast the Earth rotates, but of course we know that the one full rotation is 24 hours, so we can calculate it, but this is another measurement this is other experiment you can measure it. The keywords Foucault pendulum, plane of the motion, and it changes because of the Coriolis force. Is it okay? Yes, basically yes. The only point that the centrifugal force depends only on the angular rotation and your position in the rotating system, and the Coriolis force, sorry it's hard to see, but this is COR, the Coriolis force does not depend on your position of the coordinate system, but depends on the velocity of the coordinate system. Yes, static friction. You should start with this slide. That's what is static friction. You try to move something, but it does not move because the static friction can compensate your force. And continue here, since static friction can't be calculated, it can be calculated only by taking all the forces of the body, and if we see that static friction can compensate it, so the static friction is smaller than the coefficient of the friction times perpendicular forces, it can stop the body. If static friction should be larger than this value, it will start to move, and then we can talk about kinetic friction. So these two, 27, 28, is enough to me. circular motion in 1D. Just a minute. Sorry for the interruption. So circular motion, technically what the circular motion we talked about is two-dimensional, but if you can imagine that we can take origin, which is this line, which means theta equals 0, and if you move on the edge of this circle, your motion is one-dimensional, with the extra that sometimes you pass again the origin, again and again, and this is why we have to calculate a bit differently. But the physical quantities we have to know here is the angular displacement, angular velocity, angular acceleration, period time, the time we pass again and again the theta equals 0, and the frequency, which is 1 over period time. So I want to hear the explanation about these quantities. That's all. So it's mainly these physical quantities you have to mention. Yes, perhaps it's 1D is a bit confusing, but technically it's a one-dimensional motion. Let me change it perhaps later. I don't know. Perhaps we can skip the 1D. Describe the circular motion. Projectile motion. Wow, it's not here. So if you threw a body in 3D, you can always choose a plane in that the particle moves. So even you threw a body in 3D, you can always choose a plane. Therefore, if you choose like X and Y, this motion is a two-dimensional. If the air resistance is negligible, you can divide this motion into Y motion. This is a free fall with the initial velocity. It goes up and down. And once again, if the air resistance is 0 in X, this is just a constant speed motion. So if you calculate this free fall with initial velocity plus this constant velocity motion, you can realize that for the equation of the motion in y does not need any information from the x, and vice versa. For the equation x, you don't need anything from y except the flight time. So wait. So if you know the initial vxy, it will move like initial minus gt, and from that one you can calculate the flight time, the t. The xt equal the initial vx times t. Therefore, if you separate these two kind of motion, the time it needs to go up and down is the time when it moves along x. And these two components can describe the free fall, since when in the y projection it reaches the ground again, this is the point when it stopped its motion because it reaches the surface. So the long story is, through something in 3D, choose a plane which contains the motion. This is a 2D motion, and if there is no air resistance, you can separate the y and the x, so technically it's a 1 plus 1 dimensional motion. And you can calculate small things, so for example, what is the maximum height, this is the initial sign, etc., but you don't have to do this calculation. If you are interested, there is an interactive simulation, you can play with it. But technically, the theory is from 3D we go to 2D, and from 2D, if air resistance is negligible, you can separate it into one-dimensional motion. So this is a short story, how can we simplify your life with some with some good coordinate system. You can find longer explanation in the book. Let me copy here. This graph, of course, this is a presentation, so everything is 2D here, but technically it shows what is the x and y you should choose to have a two-dimensional motion instead of the 3D. But if you sit on your room and you throw something, that motion is three-dimensional motion. You need x, y, and z. But if you change the coordinate system according to this picture, that will be two-dimensional. Yes, that's very simple. If we want to describe a translation, we have to use the net force equal m times a. If we want to describe the rotation, it said that the net torque equal moment of inertia times angular acceleration. So instead of force, you should write tau. Instead of mass, you should write moment of inertia, and instead of acceleration, you should write angular acceleration. And the story is the same. So this equation connects the force with the acceleration, so it connects the torque with the angular acceleration. So please everybody check whether you registered for the Moodle. If you are in the Neptune course, you are allowed to register, so that will register yourself automatically. You have to, I don't know, only enroll yourself or something. So be on in the Moodle course, otherwise you won't be able to write the test 2. And after you have the test 2, I will give you the signature if you passed. The ones they forget to write the test 1 or something, I will mail them directly what to do. Non-pure rolling. If you are familiar with the pure rolling, the calculation, you know, this is a rolling situation, so we have to calculate with the rotational form of Newton's second law, but it also moves, so we have to calculate with the translational form of Newton's second law. The pure rotation means this t is small enough to not exceed this mu times perpendicular forces. That means this is a static friction. If you combine these equations, like here, you can double check whether it's standard friction or static friction or not. And it will move like the wheel on the dry road. Look, it was 0.6 here. What if I go down 0.1? 0.1 means this is a non-pure rolling, so both equations are true the translation rotation form of Newton's second law, but since it's a non-pure rolling, the friction is a kinetic friction. And that means the t is not an unknown for these three equations. It is a known. It's known at the very beginning. So technically, non-pure rolling means the touching point of the object and the surface is moving. So it's not a static point, not a static friction, but a kinetic friction. So if you know the pure rolling, you have to start to describe it and say that if it's not true that this is a static friction, the motion of the object will be non-pure rolling. It's like the wheel on the icy road. Is it better now? For non-pure rolling, the T equal mu times perpendicular force, like in the kinetic friction example in the test 1. So T for static friction, we don't know what is the T. So you can imagine if you place a box on the table, if you push it with 1 Newton and it does not move, the static friction is 1 Newton because it compensates. If you push with 10 Newton and if it does not move, the static friction is 10 Newton. But when it starts to move, the static friction will be transformed to kinetic friction, and it will be a given value like mu times perpendicular forces. So static friction is a compensating force. The kinetic friction is so-called normal force. You can calculate at the very beginning, like you calculate the weight at the beginning of the example and so on. So if you can understand the example, the box on the incline, you remember how can we calculate the static force, and when should we say that this body wheel moves along the slope? The more or less the same story. Static friction is pure rolling. Kinetic friction is for non-pure rolling. No practical question for the exam. For exam, only these questions I sent to you and what you can see on the screen right now. Any other questions according to this question catalog? And again, double check you are in the Moodle because the test 2 will be there during the time of the seminar. If no other questions, I will have another course soon. So I'd like to say goodbye and good luck for the test 2 and the exam. All the other questions should come via normal email.